Again, everyone has their own idea about how to do things. And this had to do with a problem that was, rather difficult to solve. And this problem over here. And we went through the work. Again, there's a visual over here. This is part of the work I would provide for you, and realize there's two solutions over there. One looks pretty trivial looking at. It looks like it's the number one, all right? So I can say you could check that, of course, plugging it in, and it's really not that bad to do. So let's just take a look at that, see if one works out. So 2 minus 1 is, 1. Square root of 1 is 1, and e minus e is 0, and pi to the 0 is going to be 1, of course. So this seems to work out pretty nicely. But again, I'm looking at this visual, and I'm seeing another solution over here, and I might say it looks like a half, all right? It looks like a half. Now, granted, if you plug a half in over there, I probably would say it's not going to work out too nicely, all right? So it's kind of odd that this thing here raised to some power would give you half over here. So what I did was I used a method called Newton's method to get an approximate answer to it, all right? See what the approximate was. Now, again, I say it's approximately about a half, but let me go through that with the software. All right, so what I'm going to do over here is open up a terminal. I'm going to clear the screen, and I'll explain it one step at a time. So reset, that basically gives me a clean sheet of paper. Defining x to be a variable, it's just a good habit of defining that. Now over here, I'm going to copy paste, and I want to tell you what I am copy pasting as I do it. And what I did was to use Newton's method, I have to solve this equation for 0. So how do I do that? Pi raised to the power. It looks like I did that over there. And then take away x from both sides to get 0. And Newton's method is a method that allows me to look for roots. And it's a numerical technique. And of course, I need to give it a guess. So what I do is I define what Newton's method is. I'm going to do a copy paste. Let me go back to my Sage again. And hit return. Let me explain what I got over here. So Newton's method is a function call, right? I'm defining it to be x minus f of x divided by the derivative of f of x with respect to x. And this is something, if you took Calculus 1, you've learned Newton's method, and they certainly went through the description how to derive the formula. Here's the deal about Newton's method. It's a numerical technique, and I certainly don't want to do any computations. So the first thing I do as a numerical technique is feed it a seed value. Now, someone says, what seed value would you give it? Well, you might say it's cheating. It's really not cheating. It's a numerical technique. You might as well use CUDA to do that. Is I'm looking at it, it looks like it's between 0 and 1. And I'm just going to say, off the top of my head, it looks about 0.5, right? Now, if you did f of 0.5, it should be 0 if it's true. Now, look at a crazy looking number, right? Let me approximate that. And the way I'm going to do that is .n. Whoops, sorry about that. And that's not 0. It's close to 0, but it's not 0. So what I want to do is I want to get another guess. And I'll do this over here. I'm going to assign the next guess to be Newton's method at the value x. Someone says, what's x? I assigned x this value over here. All right? What's it going to do? It's going to run through this computation to get this approximate. And I want to display the x. All right, that's a better guess, by the way. And all I got to do is keep repeating this. In other words, take that's what x is now, and just do it again. And I'm hoping that there's going to be no change, that's the best it can do. What do I notice? There's a change there. Let me do it again. I'm looking for a change. So how do you know there's a change? Just look at these numbers, and they're different. I'm not looking at everything. There's just some different numbers there. Well, look at over there. It's still changed, right? I'm going to do it again. Wow, it looks like it's not changing. Now the key about this one over here, I keep this doing over and over again, it looks like it changed a little tiny bit, but it seems like it's narrowing down to a number. Notice it's getting slower now, and I'll tell you why it's getting slower. It's really doing a tremendous number of computations. So what I want to do, I actually want to do f at that number. Get an underline there, and see what we come up with. Again, it's give me that. I got to tell it to approximate it again. And what I'm going to do over here is, let me do a copy paste. Or let me display x again. It's going to look crazy to you. Wow, that's why it's taken so long to compute. All right, so let's do this again. F of x I want to get a numerical approximation. You notice it's not struggling, but it's doing a computation, but it's taking all this stuff over here. I mean, it's really a really long set of computations it's doing over here. I mean, if you look at that, that's just a tremendous amount of numbers. I'd hate to be doing this by hand. All right? What does it give me? Wow, it gave me a number. Someone says, what is that number? That's an incredibly small number. That is incredibly close to zero. All right? That's the best my machine can do. All right? Now, granted, if you had a different machine with more precision to it, it probably could even do better than the number I'm giving it. But this is the number I just fed it, and it said, you know what? That's pretty close. And that number that we just evaluated, let me just point that out to you. Whoops. Let me display X for you in an approximate way. And again, it's computing this long number up here now, just trying to approximate it, doing every single computation. It's about a half, right? We knew that by looking at the picture, but again, according to their approximation, it's 0.491724664861606. Much better approximation. Thank you.